Hello, I'm Dominic Berry, and today I'll be talking about our latest advances in quantum algorithms for quantum chemistry using the tensor hypercontraction method, or THC for short. This work is in collaboration with people at Google, particularly Ryan Babush, who is the group leader there. I'd also like to particularly thank Junho Lee, who is the expert on the tensor hypercontraction method and did the numerics for that part. The general motivation for quantum chemistry is that it can be used to design molecules by screening many possible candidates for particular properties for applications such as pharmaceutical design, batteries, and fertilizer. Fertilizer is a particular case of interest because it relies on nitrogen fixing, which has a very inefficient industrial process. Biological nitrogen fixing is far more efficient, but is based on a complicated chemical called FeMoco, which is too difficult to simulate classically. We therefore consider this as an important test case to find the complexities of our algorithms. Next, I'll discuss the progression of the complexities of the algorithms for FeMoco. For these complexities, we are considering a number of non-Clifford gates, which are the gates which are more difficult to perform in an error-corrected quantum computer. Clifford gates, which are things like Hadamards and CNOTs, can be performed fairly easily in the surface code, but other types of gates like T-gates and Toffoli gates, which are controlled knots, need to be performed by a costly process of distilling special magic states. An important recent advance is a method of directly distilling magic states for Toffolis, shown here. That means it is useful to just count the number of Toffoli gates to estimate the cost. The first work listed here is by researchers mostly in the Microsoft group, and it found that simulation of FeMoco using simpler techniques would take about 10 to the power of 14 T-gates. Then in 2019, we found that by taking advantage of sparsity, along with a whole lot of other tricks we developed, we could reduce the complexity down to about 44 billion Toffolis. Then there was a major advance from the Microsoft group earlier this year, where they factorized the Hamiltonian to get complexity about 13 billion. In the work I'm presenting here, we reduced the complexity even further to only 5 billion, which is the best complexity yet. Next, I'll describe the general approach for these types of algorithms. Generally, what we want to do is encode the Hamiltonian as a linear combination of unitaries HL. Then the lambda parameter is the sum of the weights in this linear combination of unitaries. This lambda parameter is a very important parameter that governs the complexity of the algorithm. We construct the step of a quantum walk by using an operation P that would give a superposition state with weights that are the square roots of the WL. We then perform each of the HL unitaries on the target system where the top register controls L. Then we invert the preparation and perform a reflection about 0. Together, these operations give an operation W, which is effectively a function of the Hamiltonian in that it has eigenvalues that are functions of the eigenvalues of the Hamiltonian. We can therefore do phase estimation to estimate its eigenvalues and thereby estimate the ground state energy for the Hamiltonian, which is what we want for the simulation. Now here is the form of the Hamiltonian for these chemical systems. The first line is a standard form where the first term corresponds to 2 electron interactions and is the most important because it has the most parameters and the largest magnitude. Here n is the number of orbitals that the chemical system is represented on, and so this first line needs order n to the power of 4 parameters. The second line is the THC representation. The important parameters here are the chi and zeta matrices. The largest is zeta, which is m by m, where m is the THC truncation and scales as n. That means the number of parameters is massively reduced to order n squared instead of the 4th power of n. This reduction in the number of parameters reduces the complexity, but a problem with this representation is that it also increases the magnitude, because the value of lambda goes like this 6-fold sum over these parameters, which is significantly larger than for the original form of the Hamiltonian. To get around this problem, we group the terms together like this, so each sum over chi and A can be grouped together into these new annihilation operators C. Here I've shown it as now a sum over number operators for these new modes. These modes are not orthogonal, which would normally be a problem because it is not possible to rotate the state into the new basis of modes. But because we will be treating each of the terms in the sum in a superposition in our linear combination of unitaries approach, we can perform individual rotations for each of them, which is shown as the u nu and u mu. The really important feature of this representation is that now the lambda value is only a twofold sum and is massively reduced over what it was before. At this stage, we are still representing that operation in terms of the number operators, which are not unitary, and like I said before, we want to write the Hamiltonian in terms of unitaries. To do that, we can use the Majorana representation. First, the representation in terms of qubits is to use 1 qubit for each orbital and take it to be 0 if there is no electron in that orbital and 1 if there is. Then the fermionic annihilation and creation operators can be recombined into the Majorana operators, which are unitary. Then, using the Jordan-Wigner transform, we can write these in terms of strings of Pauli matrices like x, z, 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 z. Then, when we look at the representation of the number operators, they are just identity minus z divided by 2. Then the intrinsically two-body term in the Hamiltonian looks like this, where we have picked up an additional factor of 1/4 from the 1/2 in the representation of the number operator. That further reduces lambda. There will also be one-body terms coming from the identities inside the number operator here, which will be combined with the 1 electron part of the Hamiltonian to give an overall one-body term. Next, in order to actually perform this linear combination of unitaries, we will need to perform the basis rotations u nu and u mu. These will be controlled on registers with mu and nu from a state we prepare, and for each of these we can express them as a sequence of n simpler 2-qubit rotations called Givens rotations. This is a nice simplification because normally we would need order n squared Givens rotations to transform the basis, but here we only need to rotate the basis to orbital 1 in the correct way, which means it can be simpler. Next, to perform these controlled rotations, we use the method from the von Berg paper from the Microsoft group. We use a quantum ROM or QROM with mu or nu as input and output the angles needed for each of the Givens rotations for each value of mu or nu. Then we perform the n Givens rotations in a controlled way using the angles output by the QROM as the control. Then we perform the z on a single qubit, reverse the rotations and erase the QROM. As a result of this, we have performed the controlled operations needed in our linear combination of unitaries, but the complexity depends on the bits needed in the rotations. It's therefore important to determine the number of bits we'll need here, as well as the number of bits needed in the zeta coefficients used in the state preparation, as well as the THC truncation order m. All of these affect the complexity as well as the accuracy of the approximation of the Hamiltonian. To address this, what we did was to compute the Hamiltonian with these approximations and compare it to the exact Hamiltonian. The idea is to perform classical computation to estimate the energies and look at the difference between the results for the two Hamiltonians. We did this for two different types of orbitals. The first is a simpler set of orbitals used in the Raya paper, and the other is a newer set of orbitals proposed by a group in Caltech, which is larger but is argued to be significantly more accurate. The results shown here are only showing how the accuracy changes with the THC truncation order m. The red dashed line is the classical result for the exact Hamiltonian, and the black dashed lines show the region of precision that is aimed for in the quantum chemistry. So you can see that once m reaches about 350, there is enough precision in the simulation. Next, I show here the complete circuit for the controlled unitary part of the walk once we have encoded the two-body term and the one-body term together, which greatly saves complexity over performing them separately. Here the region in the dotted rectangle is the part encoding the one-body term. Another feature of this is that the operation is self-inverse, which is a feature which is needed for our method to work. Now here are the results for the complexities we found for the two different types of orbitals. We allowed 1 millihartree for the allowable error in the phase estimation and 0.6 millihartree for the estimated error in the Hamiltonian, for a total of 1.6 millihartree. This shows the parameters we found that give precision within 0.6 for the Hamiltonian, and we found that the complexity of the Ryer orbitals was reduced to about 5 billion, whereas for the Lie orbitals it was significantly larger at 32 billion. That is mainly because the value of lambda turns out to be larger, about 1200 here. We also performed a comparison between the THC method and previous methods, where we recomputed the complexity using the same parameters as we used here for a fair comparison. We found that in every case THC gave the lowest complexity with about a factor of 2 reduction over the double factorization approach of von Berg. We actually found that for the Lie orbitals, our previous method using sparsity even beat the von Berg method, even though it didn't for the case of the Ryer orbitals. We can also look at the complexity in terms of the number of qubits needed against the number of Toffelees. We considered a range of optimizations that reduced the number of qubits needed at the expense of a modest increase in the number of Toffelees. When we did that and worked out a layout of the quantum algorithm in physical qubits in the surface code, we estimated the whole algorithm could be done on about 1 million physical qubits in about a day and a half, provided the physical error rate was about 0.01%. To conclude, what we have found is that using THC we get the highest efficiency yet, where the efficiency is high because we have reduced the lambda value of the Hamiltonian at the same time as reducing the amount of data needed to represent the Hamiltonian. For FOMOCO, we can get the complexity down as low as 5 billion Toffelees for Ryer orbitals. Another nice feature of this work is that the projected scaling for larger systems is around n squared, which is more than a factor of n better than the prior work. This means that we expect that the improvements will be even better for larger systems. I'll just finish by pointing out the archived version of this paper here, and thanks for watching.